So for the last video in Chapter 7, we're going to talk about competition between elimination and substitution reactions. Very similar to the end of Chapter 6, when we started discussing how do we know when a reaction is SN2 versus SN1. Now we have to sort of consider how do we know when a reaction is elimination-based over substitution-based. And the answer to that is sort of very similar to, again, looking at our substitution reactions. We have to sort of consider several different factors like the nucleophile/base, solvent, substrate/electrophile, and a couple other factors as well. So let's go ahead and take a look at some of these. In short, kind of the major thing we'll have to sort of consider is whether a reaction is SN2 preferred or E2 preferred. SN1 and E1 reactions typically occur at the same pace, so there's not really a preference between them, but we'll get into that in a second here. So when we're considering these different reactions, if all the conditions favor one over the other, then we'll pretty much only have one product. But if there are conflicting conditions present, we might have a mixture, right, an equal mixture of SN2 and E2. So in general, for SN2 and E2 reactions, a strong base, right, which can also be considered a nucleophile, will favor SN2 and E2 reactions over SN1 and E1, right? Because with SN1 and E1, we typically have weak nucleophiles or bases. Steric hindrance helps favor E2 over SN2, right? And steric hindrance refers to the electrophile/substrate or the base. Polar protic solvents help favor E2 reactions over SN2 reactions. This is primarily for secondary carbons, which we'll talk about in a second. And the rates of both SN2 and E2 reactions will increase with nucleophilic or base strength. Stronger bases will give E2 preferentially over a weaker base, which will give SN2. And in general, temperature will favor elimination reactions over substitution reactions. So if you see temperature, it's a good chance you'll have more E2 product over SN2 product. It's kind of hard to say for sure if temperature will make elimination happen, E1 reactions happen more than SN1, but we'll discuss that in a second here. So what I'm going to go over really quickly is some different possible products here, right? And we'll discuss which is major and which is minor. So for this first one here, we can see that we have a primary alkyl halide, right? And we have a polar protic solvent, which we know is good for, right, these E2 reactions. And our nucleophile is a strong base. So the reason why we're going to see one reaction favored over the other is primarily because our primary carbon here is much better for SN2 reactions, okay? And we'll see this a few different times as well, where right, our major product is SN2 and our minor product is E2, right? And the reason why this is the case, especially, is because, right, remembering Zaitsev's rule, this is the worst possible alkene, right? It's not substituted at all. So that's why, in general, SN2 here will be much favored. Looking at our second example here, right, we know we have a secondary alkyl halide and same conditions, and in this case now, right, because of this secondary alkyl halide and the fact that we have our polar protic solvent, the major product this time is going to be E2. And our minor product is going to be the SN2 reaction. And this mostly has to do with the polar protic solvent, which is much better for E2 reactions, because essentially, right, it's not helping the SN2 reaction go. For a third example here, we again have a secondary alkyl halide, but now our solvent is aprotic, right, polar aprotic, which is much better for SN2 reactions. And moreover, our nucleophile here is smaller. right? We don't have these two carbons attached to it. And steric hindrance, right, our rule number 2 here, helps favor E2 over SN2, right? Even though this is not a super bulky base, the fact that hydroxy is smaller is going to help make this more SN2 anyway. And so in this case, our major is SN2, and our minor is E2. And again, mostly this has to do with the fact that we have a polar aprotic solvent, right? Which we know is better for SN2 reactions. So for our last one here, we have a tertiary alkyl halide, right? Which again, steric hindrance, right? It's a very sterically hindered carbon, and we know in general that tertiary carbons pretty much never undergo SN2 reactions. So almost by default, right, this has to be an E2 reaction. Right, and I'll say the minor product is this, but in all likelihood, this probably doesn't even form at all in solution, at least through the SN2 pathway, right? So we'll go over a lot more examples of this, but in general, this is sort of the scheme to look out for, and the deciding factors will pretty much come from solvent or kind of the steric bulk of either the base / nucleophile or the substrate. So we'll get a lot of practice with this as well. So some conclusions here, right? What we can say is for SN2 reactions, we want a strong nucleophile, but a weak base, right? And so that'll look like things like this, right? Ammonia, negatively charged iodine here, sulfur-based nucleophiles, which, right, remember from our list here, or earlier from SN2 reactions, we know that sulfur is better at being a nucleophile, right? But it is a weaker base. And then other halogens too, like bromine. Aprotic solvent, of course, also favors SN2 reactions. And minimal steric hindrance. Great, because steric hindrance will prevent the nucleophile from going into to do that backside attack. So we're mostly going to have E2 products if there is steric hindrance, right? And so reversely, right, with E2 reactions, we want a strong base, right? And steric hindrance helps as well. Right, either around the electrophilic carbon or the base. Polar protic solvent helps as well. And a high temperature. So be on the lookout for some of these factors while you're deciding whether it's an SN2 or E2 pathway. For SN1 and E1 reactions, right, because the rate-limiting step is the formation of the carbocation, the nucleophile doesn't really play any role, right, or it can't rather, because this first step to make the carbocation is just so fast. And so SN1 and E1 reactions will occur mostly with tertiary or primary substrates in polar protic solvents. And the reaction conditions will be either neutral or acidic. And like I mentioned before, it's hard to influence what type of products are formed, right? Because the nucleophile and base are not involved in the rate-limiting step. And so we're always going to get some mixture of E1 and SN1 reactions. I might give examples where temperature will favor E1 reactions over SN1 reactions, but in general, right, it's hard to say whether one is favored over the other, so you can always assume it's going to be a mix with neither really being the major product, okay? I might give an example where we might see E1 favored, and it'll mostly be due to temperature, but in general you don't really need to worry about that, and always assume there is an equal mix of E1 and SN1 reactions. So to cap things off here, let's look at a substrate table, or rather, right, kind of our electrophile table. where L stands for leaving group. Okay, so there's L in every case here, right? So for methyl substrates, right, just an alkyl halide with only a methyl group attached to it, these are basically SN2 only, right? There's no way to even form an alkene product. So by default, SN2 is the only thing that can happen, right? Because SN1 reactions would not go through this pathway because methyl carbocations are the worst possible kind of a carbocation. So for primary substrates, mostly SN2, right? Again, we can't really form SN1 reactions here, but it can be E2 favored with a bulky base, heat, and protic solvent, or polar protic solvent. And so for secondary carbons, as we've seen before, this is kind of where the most reasoning has to come into place to determine whether one is favored over the other. And so we can get some sort of a mix of SN2 and E2 reactions, and or SN1 and E1 reactions. So if the SN2 reaction is favored, very similar to the last page here, it'll have to be because of a strong nucleophile that is also a weak base, has to have low temperature, and an aprotic solvent. E2 reaction will be favored when you have a strong base, you have heat, steric hindrance, either of the actual carbon in question or the base itself, right, a bulky base. And you'll want to have a protic solvent. So for SN1 and E1 reactions, right, we'll have to have a polar protic solvent, which we can see is similar to E2, right? So how do we know if it's E1 versus E2? And that comes from having a weak base, right? So not a negatively charged oxygen, but something that's neutral. And it'll typically be under neutral or acidic conditions, right? Like the H2SO4 dehydration reaction we talked about. So the big difference to look out here for E2 versus an E1 mechanism is that weak base, right? Because the weak base will help promote the loss of the carbocation, while a strong base might go ahead and pull off that hydrogen right away without the formation of the carbocation intermediate. So for tertiary, there's still some difference here, but not as much. SN2 reactions basically don't happen. For E2 reactions, right, we know that our tertiary carbon is pretty bulky, so this E2 reactions will occur with a strong base. SN1 and E1 reactions will occur, kind of as we already discussed, with a weak base. Or with neutral and acidic conditions. So the big thing to look out for here with tertiary carbons is whether it's a strong base or a weak base. If it's a strong base, you know it'll be primarily E2 reactions. And if you have a weak base, right, a base that isn't negatively charged, essentially, you know that we will be going through an SN1 and an E1 mechanism. Right, so kind of a lot of things to take in here, but hopefully as we do some more examples, which we'll go ahead and do in lecture, we'll be able to better differentiate between an elimination and a substitution reaction and which type is actually occurring, and if there is a mixture or if one is primarily preferred over the